The universe is vast and ever-changing. Within its inky blackness lie incredible wonders. Among these wonders are stars, the building blocks of galaxies and the cradles of life itself. But where do these celestial giants come from? The answer lies in cosmic nurseries, vast clouds of gas and dust known as molecular clouds. These clouds are not uniform. They are wispy and ethereal with regions of varying density. Deep within these clouds, gravity plays a crucial role. It draws together particles of gas and dust, pulling them closer and closer. Over eons, these clumps of matter grow larger, their gravitational pull intensifying. These are the seeds of stars, destined to illuminate the cosmos. As we explore further, we'll uncover the secrets of stellar evolution. We'll witness the birth, life, and death of stars, each stage a testament to the awe-inspiring forces at play in our universe. Join me on this journey as we unravel the mysteries of the cosmos, one star at a time. Deep within the heart of molecular clouds, a cosmic ballet is underway. Gravity, the master choreographer, orchestrates the movements of countless particles. Atoms of hydrogen, helium, and heavier elements dance closer, drawn together by an irresistible force. As these particles coalesce, they form a dense core called a protostar.
The protostar is not yet a true star. It is a swirling vortex of gas and dust, its core growing hotter and denser with each passing moment. The immense pressure at the center generates heat, causing the protostar to glow with an eerie infrared light.
As the protostar continues to accrete material, its temperature and pressure climb steadily. This process of gravitational collapse is a slow and steady one. It can take millions of years for a protostar to gather enough mass and reach the critical temperature needed to ignite nuclear fusion. But once fusion begins, a star is truly born. The birth of a star is a momentous occasion, a cosmic explosion of energy that illuminates the surrounding nebula. At the heart of a protostar, temperatures and pressures reach unimaginable levels. Hydrogen atoms, forced together by immense gravity, overcome their natural repulsion and fuse. This process, known as nuclear fusion, releases an incredible amount of energy. The energy released by fusion creates an outward pressure that counteracts the inward pull of gravity. A delicate balance is struck and the protostar stabilizes. It is now a main sequence star, powered by the continuous fusion of hydrogen into helium in its core. This is the longest and most stable stage of a star's life. The moment of stellar ignition is a pivotal turning point in the life of a star. It marks the transition from a collapsing cloud of gas and dust to a true celestial powerhouse, radiating light and heat across the cosmos. Once a star achieves nuclear fusion, it enters the main sequence, a period of stability and brilliance. This is the longest stage in a star's life, during which it steadily converts hydrogen to helium in its core, releasing a constant stream of energy. Our own sun is a main sequence star, and it has been shining brightly for billions of years. The lifespan of a star on the main sequence is determined by its mass. Massive stars with their larger fuel reserves burn brighter and hotter but have shorter lifespans. Smaller stars, on the other hand, are more frugal with their fuel, leading to longer but less luminous lives.
These cooler, dimmer stars are known as red dwarfs.
During its time on the main sequence, a star experiences a delicate balance between the inward pull of gravity and the outward pressure generated by nuclear fusion. This equilibrium ensures the star's stability, allowing it to shine steadily for millions or even billions of years.
As a star exhausts the hydrogen fuel in its core, its time on the main sequence comes to an end.
Without the outward pressure of fusion to counteract gravity, the core begins to contract.
This contraction heats the core even further, causing the outer layers of the star to expand dramatically.
The star swells in size, becoming a red giant.
Red giants are much cooler than their main sequence counterparts, giving them a reddish hue.
Despite their cooler temperatures, they are incredibly luminous due to their enormous size.
Some red giants, like Betelgeuse in the constellation Orion, are so large that if they replaced our sun, their surface would extend beyond the orbit of Mars.
The red giant phase is a time of significant change for a star.
As the core contracts and heats up, it eventually becomes hot enough to fuse helium into heavier elements, such as carbon and oxygen.
This process releases additional energy, temporarily prolonging the star's life. Section 6. Supergiants, harbingers of doom. For stars significantly more massive than our sun, The red giant phase is just a prelude to an even more dramatic transformation. These stellar behemoths continue to fuse heavier and heavier elements in their cores, progressing through a series of nuclear reactions that produce elements like neon, magnesium, silicon, and iron.
As the core becomes increasingly dense and packed with heavy elements, it reaches a critical point. Iron, the most stable of all nuclei, cannot be fused to release energy. Fusion ceases, and the outward pressure that once supported the star against gravity vanishes.
The core collapses in a fraction of a second, triggering a catastrophic explosion known as a supernova. Supergiants are harbingers of cosmic doom. Their immense size and luminosity are testament to the incredible forces at play within them. Their eventual demise in a supernova is one of the most spectacular events in the universe. Section 7. Stellar demise fading to white dwarfs. For stars like our Sun and those smaller, the end is a more gradual affair. As a red giant exhausts its remaining fuel, it sheds its outer layers into space, forming a beautiful expanding cloud of gas and dust known as a planetary nebula. These nebulas are often illuminated by the dying star at their center, creating some of the most breathtaking sights in the cosmos. At the heart of a planetary nebula lies the star's exposed core, a small, dense object called a white dwarf. White dwarfs are incredibly hot, but they no longer produce energy through nuclear fusion. Instead, they slowly cool over billions of years, eventually fading away into faint stellar embers. While white dwarfs may represent the end of a star's active life, they are far from insignificant. These stellar remnants continue to exert a gravitational pull on their surroundings, and their interactions with other objects can lead to the formation of new celestial bodies. Section 8. Supernovae, the grand finale. Supernovae are among the most energetic events in the universe, outshining entire galaxies for a brief period. When the core of a massive star collapses, it unleashes a shock wave that tears through the star's outer layers, propelling them into space at incredible speeds.
This explosion releases an unimaginable amount of energy, including visible light, X-rays, gamma rays, and a torrent of subatomic particles. Supernovae are not only destructive events, but also crucial for the evolution of the universe.
The intense heat and pressure generated during a supernova explosion create elements heavier than iron, such as gold, silver, and uranium. These elements are scattered into the interstellar medium, enriching future generations of stars and planets. The remnants of a supernova explosion can take many forms. In some cases, the core of the star survives as a neutron star, an incredibly dense object composed almost entirely of neutrons. In other cases, the core collapses further, forming a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Section 9. Stellar remnants, legacies of light. Even in death, stars leave behind legacies that shape the universe around them. White dwarfs, neutron stars, and black holes, the remnants of stellar evolution, continue to exert their influence on their surroundings, sometimes in dramatic and unexpected ways.
White dwarfs, though small and faint, can still accrete material from companion stars, leading to nova explosions or even the complete destruction of the white dwarf in a Type Ia supernova. Neutron stars, with their incredibly strong magnetic fields and rapid rotation, can emit beams of radiation that sweep across the sky, making them visible as pulsars.
Black holes, the most enigmatic of all stellar remnants, warp spacetime to such an extent that they create regions from which nothing can escape. Their immense gravity can disrupt the orbits of nearby stars and even devour entire star clusters. The study of stellar remnants provides invaluable insights into the life and death of stars and the fundamental laws of physics that govern our universe. These celestial objects, once shining beacons of light and energy, continue to captivate and inspire us, reminding us of the vastness and wonder of the cosmos.
Thanks for watching Fam Spectrum. Like, comment, and subscribe for more fun. Hit the bell icon to never miss an update. See you in the next video. Bye.